My name is Safia. I'm a software engineer and a longtime open source community member. In this talk, you and me will learn all about HTTP. As a note, this talk contains an optional interactive portion. If you're interested in following along, you'll need to make sure that you have a web browser like Chrome or Firefox installed on your machine and that you're familiar with the web browser. So, what is HTTP? HTTP is one of the protocols that underpins the inner workings of the internet. A protocol is a set of rules that describes how data should be exchanged between two devices, such as your computer and a web server, or a USB and a device. There's a variety of different protocols that are used in the web for facilitating everything from exchanging emails to uploading files to chat messaging. In this talk, we'll be covering HTTP. HTTP stands for HyperText Transfer Protocol. Let's break down what this is by going through each word. We've already covered what protocol means, but what about the other terms in this acronym? Hypertext is text that contains references to other documents with hypertext. These references are typically called hyperlinks. So text with hyperlinks is hypertext. Every piece of content that you visit on the web is some sort of hypertext, whether it's a news article or a tweet or a Facebook post or an Instagram post. It's likely that it contains links or references to other images, websites, or documents on the web. The transfer part lets us know that this protocol relates to the way that hypertext is exchanged between devices. The best way to explore how HTTP works is to get hands-on with it. What happens when you visit a website like github.com or google.com? One of the prerequisites of this talk was having a web browser like Chrome or Firefox available to you. I'll be doing this exploration in Chrome. The experience would be similar if you used a browser like Edge and rather similar if you use a browser like Firefox. The general gist will follow. Again, this exercise is optional, so if you just want to follow along and listen, you're welcome to do that. Most browsers come with developers' tools that allow you to explore the HTTP requests and responses that occur during the lifetime of the web page, inspect the contents of the web page's hypertext, profile web pages, and more. We'll use developer tools to do a hands-on exploration of HTTP. To get started, we'll open a new browser window in our browser of choice and open developer tools. Then we'll visit our website of choice, github.com. In the network tab, we can view a list of outgoing requests and their responses. Requests and responses are a big part of the crux of HTTP. The request-response process starts with a web browser on one end and a web server on the other. The web server hosts the hypertext documents that the web browser will display to the user. The web browser sends a request to the user, and the server returns a response. Request, response, browser, server. It's important to note that while a web browser is usually the client that's sending out the HTTP requests, that's not always the case. Another example of an application that uses HTTP to communicate with a server is an Instagram application or a Facebook application. They're not web browsers per se, they're native apps, but they still send HTTP requests to fetch resources from a web browser or a web server. So what do these requests and responses look like? First things first, the request contains a method highlighted here. HTTP methods allow the browser to tell the server what type of the request they would like to make. The request highlighted here is a GET request, which indicates that the browser wants to get a document that this host is providing. There's a couple of other types of requests, including POST requests, PUT requests, and DELETE requests. One thing you'll notice is all request methods are verbs that describe the action that you want to achieve with the web server. For example, a GET request says that you want to get information from a web server. A POST request says that you want to post information to a web server. And a DELETE request says that you want to delete some information or some resource that exists on the web server. Each HTTP request and response also comes with a set of headers. HTTP headers are key value pairs that web browsers and servers use to exchange additional information. The headers can be used to indicate the type of resource that was transferred, what kind of HTTP connection it was transmitted over, and more. There's 3 different types of HTTP headers. The first category is required headers. Required headers are mandated by the HTTP specification to exist in both the request and the response. Typically, these are headers that outline the date that a request was sent or what type of data was transmitted over it. The second type of HTTP headers are optional headers. These exist as part of the HTTP specification, but aren't required for all requests or responses. Typically, these will be used if you want to enable some sort of custom feature, like compressing the HTTP response that's transmitted. The third type of HTTP header are custom headers. Custom headers are defined by a particular web application. For example, I might build a web app that queries a custom API. I can introduce a new HTTP header that outlines what API version a particular client is communicating with. These three types of headers get at a really important aspect of HTTP. It's extensible. In addition to the standard headers that are required by the specification, web developers can introduce their own headers to fulfill custom business requirements. This has actually been a pretty big deal throughout the evolution of HTTP. Because developers can introduce their own headers, what tends to happen is that a developer will introduce a header to fulfill a particular requirement. That idea catches on, more developers introduce that custom header, and then eventually it becomes a part of the specification. This was something that happened quite frequently during the early days of the evolution of the HTTP specification. Now, the request and response process is broken down into a set of steps, starting with when the request is queued, to when it is sent, to when the response is processed. Here we can see that it takes 102.60 milliseconds for a single request to be processed. Now, you might imagine that if each web request was sent one after the other, it would take quite a long time for a single web page to completely load. Think about it. You open up Instagram and Twitter, there's tons of messages, texts, videos, links. You'd have to send each request for a picture or a video one by one, waiting to receive a response from the previous request before you can send the next one. This phenomena is illustrated in the image to the right, where there's no pipelining. You can see that requests are sent successively, each waiting for a response. And it takes a relatively long time for a single response to be processed. But pipelining comes into the rescue. HTTP pipelining is a feature where multiple requests can be sent at the same time, and their responses can be processed separately. You can see how this works on the image to the left. A client will send off 3 requests all at once for different assets, and then wait for the responses and process them individually. It dramatically reduces the amount of time it takes to load up a web page. Instead of waiting eons to get all of the images and videos on your feed, you're probably just waiting a few seconds. These types of performance optimizations and features are a critical and unsung part of HTTP. They help make the web what it is, and indeed a lot of the interesting innovation in the HTTP protocol, or in HTTP, is in these types of performance improvements. Of course, performance isn't the only thing that we need to worry about as developers. Security is an important aspect as well. In addition to providing support for pipelining to improve the performance of the protocol, HTTP allows users to secure the transmission of hypertext documents using HTTP and TLS, Transport Layer Security, another protocol that we covered in our cloud of protocols earlier in the talk. Let's go back to this word cloud, because there's something interesting here. It might seem like a chaotic blur of different acronyms all glued together in one place, but that's not really the reality. There's actually a little bit of a structure to the way that these protocols interact with each other. They're layered in a layout that is conceptually referred to as the network stack. At the bottom of the network stack, we see protocols like TCP and UDP that deal with making connections between two devices. In the middle of the network stack, we see protocols like HTTP and FTP that deal with the way applications speak with each other. Applications in this case are web browsers and web servers, or email clients and email servers. And then at the top of the network stack, we see protocols like TLS that are designed to work in synchrony with other protocols to introduce features like security. So typically when we look at something like HTTPS, what we're actually seeing is TLS, which is the protocol that outlines how messages should be encrypted and how user identity should be authenticated. TLS is applied to HTTP, which is a protocol for transmitting messages that we just covered in this talk. Finally, HTTP messages are transmitted over a connection that is created and maintained using TCP, the Transmission Control Protocol. All of these protocols are responsible for different aspects of the connection. TLS for security, HTTP for message exchange, and TCP for maintaining the connection. The beauty of the network stack is that each of these protocols has a unique responsibility, but they can work together collectively to provide functional applications. With this in mind, let's cover a few fast facts on HTTP. HTTP is a protocol that facilitates the transmission of data between a client, like a web browser, and a server. HTTP is a request-response-based protocol. It outlines the types of messages that can be sent as requests and the message format of the expected response. Each request contains headers that can be used to exchange additional information about the request. Headers are also a pretty powerful extensibility point for HTTP. Developers can introduce custom headers that they need to fulfill the business requirements of their applications. And if a header is general and useful enough, it can become widely adopted and even eventually become a part of the specification. HTTP provides support for performance and security through features like pipelining and HTTPS. Performance is a key aspect of the evolution of HTTP. As the web grows more popular and web developers build more complex web applications that need more resources like rich images, graphics, videos, scripts, a performant protocol is important for the evolution of the web. And finally, HTTP is one of the many protocols that fits into what's known as the network stack. The network stack is a conceptual model for how different networking protocols interact. Each network stack layer indicates a particular type of requirement that's fulfilled by the protocols. For example, the layer where TCP and UDP live outlines how connections will be established. The layer where HTTP lives outlines how applications communicate with each other. This layering makes it clear what the different responsibilities of each protocol are and how they can work with each other to facilitate what we know as the web. That's it for me. With all this in mind, I'm opening it up to you for questions. Feel free to ask anything about material that was covered and further details on some of the general points that were conveyed. Thank you so much for having me here at Codeland, and I hope you enjoyed this presentation and the other talks that you'll be attending.